So, in our last discussion we looked at a few examples of drift, and I said that if we are to go beyond in this topic, we need to figure out some ways by which we can measure the effect of genetic drift. Now, the simplest way of getting a foothold into this is through this concept of heterozygosity. Now, what exactly is that? So, in order to understand that, let us go to our favorite simulator. Here we are, and we say start tool, and simulations we go to replicated simulations. So, since we are trying to study drift, we will reduce the population size. Let us say we have a population size of 10, and let us say we have generations, we can make it 200, good enough. Starting allele frequency 0.5 is fine, and let us say we start with 10 populations, and we say run simulation. What do we see? As expected, we find that sometimes allele A1 gets fixed, sometimes allele A2 gets fixed. No surprises there, that is what you expect out of drift. Now, the problem is, because we do not know whether A1 will get fixed or whether A2 will get fixed, if you track any one of them, either you track P or you track Q, their frequencies, sometimes it will go up, sometimes it will go down. However, there is one thing whose frequency is in general always going to go down, and that is the frequency of the heterozygotes, the heterozygosity. Why do I say so? Now, in this particular case where I am showing you the genotypic frequency, unfortunately they are giving me the genotypic frequency only for the last simulation, right. But you can clearly see that the green one, this is the frequency of the heterozygotes, you can see that it is falling. Why will that happen? Very easy. We know that the ultimate fate under drift is either that the allele will get fixed or it will get lost. In either case, P will either become very high, go to 1, or become very low, go to 0. Now, we know that the frequency of the heterozygotes is 2 pq, and we also know that that gets maximized when P and Q are close to each other. Actually, P and Q, given that both of them are between 0 to 1, the quantity gets maximized when P equal to Q equal to 0.5. But the important part is, if either P or Q goes down, then the heterozygosity, which is the frequency of the heterozygotes, also has to go down. So, that is a simple concept, that whenever an allele is going due to drift is going towards fixation or loss, the frequency can go up or down, but heterozygosity of the population will always go down. So, with this extremely simple concept, we can now go back to our PowerPoint, which is here, and yeah. So, here I talked about the fact that when the population is going towards fixation or loss of an allele, then the heterozygosity is going to be reduced. Now, there are multiple ways in which this can happen. Of course, sampling size due to small sampling error due to small population size or drift is one reason, but other things can also happen. So, for example, suppose you have mating between close relatives, then as we are going to see in one of our subsequent discussions, that can also lead to in general increase in the homozygosity in the population, and therefore a reduction in the fraction of the heterozygotes. Similarly, if you have selection happening, then that also can push one allele's frequency close to 1 or 0, as a result of which again the frequency of the heterozygotes in the population will go down. Therefore, although drift by itself in the long run will reduce heterozygosity, a reduced heterozygosity does not necessarily imply that drift is happening. There are other things also that can reduce heterozygosity. Okay. So, now the other major thing to keep in mind is, what do we mean by heterozygosity? Now, I gave you a definition which is the fraction of heterozygotes in the population, and that is the correct definition. But turns out that, like many other concepts in ecology and evolution, the term heterozygosity is also used in multiple contexts, and therefore, you have to be a little careful when you read the word heterozygosity in the literature, some of them might mean it in a slightly different context. Often it becomes clear just by reading the context what exactly they are talking about, sometimes it does not, so you have to be careful. But anyway, in the context of our discussion for this course, we are going to stick to heterozygosity as fraction of heterozygotes in the population. Now, here we have a problem. I have been saying that heterozygosity going low, but how exactly am I defining low? I mean, low, high, these are all relative terms, right? They have to be defined in the context of something else. So, compared to what? How low is low? So, turns out that the comparison is always in the context of something known as an ideal population or an idealized population. Now, what exactly do you mean by that? So, many places they simply say a population which is following all the assumptions of Hardy-Weinberg equilibrium, that is an ideal population. That is actually a wrong definition. So, an ideal or an idealized population in the context of genetic drift is supposed to have the following properties. First, we assume that all the individuals are hermaphrodites. In other words, all individuals are able to produce both male and the female gametes, and mating is random, which basically means that any male gamete can fertilize any female gamete, but in this particular case self fertilization is explicitly allowed. So, in real life biology there are many cases where self fertilization never happens, but in the context of an idealized population, remember it is a theoretical construct, in that context you assume that self fertilization is allowed. And of course, you have no mutation, no migration, no selection. This part is exactly as Hardy-Weinberg. But then the last point, this is the crucial one, the population size remains constant across generations. Okay, it does not change and it is finite. This is very, very important. So, now that you have defined an idealized population like this, obviously some of you are thinking that why exactly am I taking these assumptions and not other assumptions? So, the reason you need precisely these assumptions has to do with how you do the derivation. Okay. We are not going to look at the derivation in the context of this particular course, which is why it becomes a little difficult to see where these assumptions are coming from. But many of you will probably end up taking an advanced course, and at that point you will do the derivation for heterozygosity and or rather change in heterozygosity over time, and at that point this will become clear that why precisely you need these assumptions and not others. So, anyway, now that we have defined a ideal population, we have established a benchmark against which we are going to compare, we can now ask the question that what is the size of the ideal population, how many individuals are there in the ideal population that undergoes the same amount of drift as the population that I am interested in, the focal population, the given population. Okay. This size of the ideal population which undergoes the same amount of drift as my population of interest, this size is known as the effective size of the given population. Very important. The effective size is a theoretical construct. It is the corresponding size of the ideal population which is undergoing, it is a number of individuals in an ideal population that is undergoing the same amount of drift, and this particular case we are going to say it is losing heterozygosity at the same rate as the population of my interest. Now, please appreciate that when it comes to understanding about drift, you can think in terms of heterozygosity, but there are many other quantities in terms of which drift can also be defined. And since you can define drift in terms of other quantities, you can also define your effective population sizes in terms of those quantities. Okay. So, there is no one effective population size in the literature. There are multiple kinds of effective population sizes in the literature, and depending on which definition you are looking at, for the given population you can have multiple effective sizes, right. I mean, that should not be too tough, because if you are thinking in terms of how fast it is losing heterozygosity, you think in terms of the heterozygosity kind of effective population size. If you think in terms of how fast its variance is changing, variance of alleles, then you think in terms of what is known as the variance effective population size, and so on and so forth. So, there are some 3 or 4 types, and depending on which quantity of drift, which aspect of drift you are interested in, you end up getting a different estimate of your effective population size, and all these effective population size of values can be very, very different from each other. Typically, not always, typically the value of the effective population size is less than the census size. However, in many cases it can even be greater than the census size, depends on which concept you are using and under what context you are measuring it. Anyway, so that is the that is a underlying conceptualization, theorization of effective population size, but in order to actually measure it, you need to have some numbers, right. So, now I will talk about 2 or 3 different measures that are often used. So, for example, suppose you have a population, just one population, and you want to know as of this moment what is its effective population size. You are not interested in knowing how it is losing heterozygosity or some other quantity, you want to know then and there what is the effective population size. So, if you have a scenario like this, then typically for sexually reproducing organisms, the formula is given like this: effective population size NE equal to 4 NF into NM divided by NF plus NM, where NF is how many females are there and NM is how many males are there. Now, if you just look at this expression, certain things should be very clear to you. You can see that what you have in the numerator is a product NF and NM, and what you have in the denominator is essentially the total population size NF plus NM. Now, for any given total population size, the closer is the value of NF to the value of NM, the larger is going to be the product, the numerator, and therefore, the larger is going to be the NE. In other words, if you have a population in which the number of males and females are hugely different, let us say just a random example, let us say there are 100 males and only 2 females, or there are 200 females and just 5 males. In all those cases, the effective population size is actually going to be much lower than the census size, simply because that product is going to become small. Whereas, the same 100 individuals in the population, instead of having say 90 plus 10, if you have say 50-50, then the product on the top becomes 15 to 50, 2500. Okay. Of course, multiplied by 4 and so on, but the product above becomes, in the numerator becomes large, whereas if it is say 90 plus 10, it becomes 90 to 10 equal to 900, right. So, that is what I mean by saying, if the population, in the population the males and the females are in equal numbers, then the effective population size is the highest, and any deviation from the 1:1 ratio actually leads to a reduction in the effective population size. The second way of very commonly used way of measuring effective population size, when you are assuming that males and females are in the same ratio 1:1, or let us say you are thinking in terms of asexual populations in some cases, then across multiple generations the effective population size is given by this formula T by 1 by N1 plus 1 by N2 plus up to Nt, where T is the time. So, N1 is population size at generation 1 or time step 1, N2 is population size at generation 2 and so on. So, you can see that this is the formula of the so called harmonic mean of the population sizes over generation. So, it is a property of the harmonic mean that they get affected more by lower values of n than by higher values of n. Okay. And therefore, when are you going to use this kind of a formula? You are going to use this kind of a formula when, let us say, a population's size is fluctuating over generations, and you want to know that over the entire period of time, what is the one value which I can say is the effective population size. And you can see that each time it is going down, okay, due to the property of harmonic mean, each time it is going down, the low values are going to have a disproportionate effect on the harmonic mean than the higher values, which is why when you have a population whose size is fluctuating over time, it is the population crashes which end up affecting the effective population size more than the population booms. And finally, remember we were talking about heterozygosity or loss of heterozygosity. So, the formula for the loss of heterozygosity is given as Ht plus 1 equal to Ht into 1 minus 1 by 2 Ne, where Ht is the heterozygosity at generation T, what fraction of the population is heterozygotes at generation T, and Ne is the effective population size. Again, if you look at this formula, straight away you can see certain things. Ht plus 1 equal to Ht multiplied by something. So, heterozygosity at generation T plus 1 is previous generation's heterozygosity multiplied by that thing 1 minus 1 by 2 Ne. Now, look at 1 minus 1 by 2 Ne. The larger is the value of Ne, the smaller will be 1 by 2 Ne, because Ne is in the denominator, and the smaller is going to be 1 by 2 Ne. This 1 minus 2 Ne is going to be larger, right. I mean 1 minus 2 Ne will always obviously lie between 0 and 1. So, 1 minus 2 Ne will become larger, and therefore, Ht plus 1 will be a bigger fraction of the previous generation's thing, previous generation's heterozygosity. In other words, the smaller is the value of Ne, the faster is heterozygosity lost, the larger is the value of Ne, the slower is heterozygosity lost. Now, I am not giving you the formula over here, the derivation of the formula over here, simply because that is not a part of a basic course, but anybody who is more mathematically inclined and would like to see for themselves how this comes, just go to this particular link. This is the course note of somebody, and it is not a part of the course, but you can assure yourself that this comes out of proper mathematical logic. This particular equation that you are seeing, this is known as Sewall-Wright's equation of genetic drift, the same Sewall-Wright whose viability selection equation we looked at. So, with this understanding, we can now revisit our Bury's experiment which we saw in our previous discussion. So, remember in Bury's experiment we started with 107 populations, all of which were explicitly made out of heterozygotes, and then over time we saw that the genetic composition of the populations started diverging from each other, and by generation 19 you had about 30 populations in which the allele, in this particular case BW75, was lost, and around 28 populations in which this BW75 allele was fixed. Okay. So, this is the classic case of drift. Now, obviously, when you have these two extremes in generation 19, when one allele is fixed in 32 populations, 30 populations, the other is fixed in 28 populations, then obviously the overall heterozygosity of the population has gone down drastically, right. But as you can see, that has not happened in one generation, it has happened over time. So, how exactly does the thing proceed? So, here is the graph. So, here on x axis we have generation, okay, 0 to 19, and on y axis we have the average heterozygosity, right. So, what is across 107 populations, what is the average of the heterozygosity, and that data is plotted in this thing in the middle curve in green, okay, the one that is bouncing around. And you can see that I have also plotted two other lines. The first line is theoretical Ne equal to 16. What is that? That is simply this equation where I have fit Ne to be equal to 16 and I have put Ht as the first generation's heterozygosity, and I have simply simulated it, and that has led to this line. Okay. So, theoretically speaking, if my Ne were to be 16, then this is what the way the heterozygosity should have come down. Now, why did I choose Ne equal to 16? That is because remember in this particular population, Buri had kept the population size constant at 8 pairs, 8 males plus 8 females throughout the experiment, which is why I am assuming that the census size is equal to the effective population size, hence n equal to 16. And I have done the same thing for this blue line below, except that here I have ended up taking theoretical n equal to 9. And now I want to compare the green line, which is the way the heterozygosity actually went down, with the orange line and the blue line. And what do I see? That although initially it looked as if the heterozygosity, the reduction in heterozygosity was similar to the n equal to 16 curve, but very soon it actually became much closer. Towards the later part, it completely, I mean not completely, to a great extent it overlaps with the n equal to 9 line, which essentially means that in the long run this population is behaving as if it has only 9 individuals of the idealized population. Okay. And that is why we say that the effective population size in the context of Buri's experiment was only 9, even though the census population size was 16, right. So, this gives us some idea about how we can measure the effect of drift in real life data. Now, with this information, we are now going to ask the question that what exactly does drift do to a population when it is interacting with other evolutionary forces. Remember, in real life drift never operates alone, nor does selection for that matter typically. So, in real life drift has to interact with selection. So, what really happens when this interaction happens? And the example that we are going to look at will be in the context of evolution of mutation rates. Now, as we all know that there is a tremendous variation in mutation rates across all life forms. So, for example, if you look at simple bacteria like E. coli, they have a mutation rate, per base substitution mutation rate roughly of the order of 10 to the power minus 10. Whereas, if you take something like Drosophila melanogaster, it is about 10 to the power minus 9. Homo sapiens, that is us, 10 to the power minus 8, and all the way up to the viruses, which can go as high as 10 to the power minus 5 or 10 to the power minus 4. So, comparing between bacteria to virus, you have everything going between 10 to the power minus 4 to 10 to the power minus 10, that is about 6 orders of magnitude. That is a very large amount of variation. Now, we have already discussed that most of the mutations which actually end up affecting the organism, they are either deleterious or they are lethal. So, if that be the case, then there should actually be a very strong selection against mutation rates. However, if that be the case, why do you expect to get, or why do you get that tremendous variation that we actually saw? Why does not the mutation rate evolve to become 0? So, this was the very famous question asked by Sturtevant. So, this is the person who figured out that you can use the recombination rates to map the distances between loci on a chromosome. He did that when he was a teenager, an undergraduate, which ultimately led to a Nobel Prize. And of course, he made many other contributions, but he also ended up very succinctly putting the question, why does not the mutation rate evolve to 0? So, there can be multiple hypotheses in this context. We are going to deal with just one or two. So, one possibility is that there exists a cost of fidelity with replication speed. Now, what do I mean? Now, we know that different organisms, their cells are replicating at very different rates. Some like bacteria, they are probably replicating every 20 minutes or so on an average, whereas humans or some other cells, they are replicating at a much slower pace. Now, we know that whenever a cell is replicating, it needs to create copies of its DNA. Now, we also know that this copying process is actually, replication process is actually error prone. So, when the bases are being inserted by DNA polymerase, sometimes it ends up incorporating wrong bases. But fortunately, there are multiple mechanisms by which these errors can be corrected. So, for example, DNA polymerase itself has the ability to go back and take out a wrong base and then go forward. So, the hypothesis is that if you having a speed requirement, you need to replicate fast, then if you every time wrong base is incorporated, DNA polymerase has to go back and then change it, then obviously that is going to slow it down. In other words, that is going to negatively affect the replication speed, and therefore the entire variation that we see in mutation rates. So, different organisms, they replicate at different rates, and therefore they have different degrees of tolerance towards how much they can do in terms of error correction, and because of that variation you get that entire variation in mutation rate. Now, what is the problem with this logic? The problem with this logic is that if this were indeed correct, then you expect that all those guys who are replicating very fast, they are the ones who will be paying the cost of replication and in terms of speed, and therefore they are the ones who will have the maximum mutation rate. In other words, you expect the bacteria, for example, to have a very low mutation rate, very high mutation rate, whereas in reality you see exactly the opposite. As I showed you in that particular chart, bacteria have much lower mutation rates than say vertebrates, whereas it is the vertebrates which replicate much slower than the bacteria. So, obviously this is not going to work out. So, another hypothesis is that after all these error corrections, these are all physicochemical processes, and all physicochemical processes will have some upper limit. Okay, we can only correct mutations up to this limit and not further. Okay, not every mutation can be, or not every error can be corrected, and because of selection all organisms have actually ended up reaching the physicochemical limit of this accuracy of replication and repair, and therefore no further changes can be done. Great, but here we have a problem. The problem is that as far as we understand, the chemistry of replication and all these processes is remarkably conserved across all taxa. So, if that be the case, if these limits are indeed due to physicochemical reasons, then they should be similar across all taxa. If they are similar across all taxa, you expect some mutation rate, but you expect that mutation rate to be the same everywhere. You actually do not expect to see the huge amount of variation that I ended up showing you. So, that tells us that perhaps this hypothesis is not a good explanator for why, or not a good explanation for why there exists so much of variation. So, as I said, there are many other hypotheses and one can examine them if one is in an advanced course. So, we will not go into those, we will go straight into a hypothesis which as of this moment seems like the most credible one, and this is the so called drift barrier hypothesis. So, what does it say? So, it says that selection is continuously trying to reduce the mutation rate in populations. However, the effectiveness of selection depends on the amount of drift that is being faced by the population. If you have high drift, then selection's ability to, let us say, increase or decrease the frequency of some alleles is going to be compromised, and therefore we also know that how much drift a population is experiencing is inversely proportional to its effective population size, the so called NE. Therefore, the whole idea is that species which have lower NE, they will end up evolving higher mutation rate because selection is not very effective in them, whereas those which have a higher NE, they will end up having lower mutation rate. Now, understand something, that effective population size is not a property of the species by itself. Effective population size, I mean, part of it is a property, it is a property of the physiology, but part of it is also very ecological. It depends on how much resources it gets, it depends on who else is there in the same resources, and so on and so forth. Therefore, this hypothesis is saying that look, due to ecological reasons, organisms will end up having very different kinds of effective population sizes, and those with higher effective population sizes will have lower mutation rate and vice versa. So, just to show you the same thing graphically. So, here this is just a cartoon. Okay. We have effective population size on x axis and you have a trait like mutation rate on y axis. Now, selection is trying to bring the mutation rate down, and selection is more effective when the effective population size is high. So, the length of the green arrows, they are showing you the effectiveness of selection, and it is clearly showing that when effective population size is high, selection is more effective, and that is why the trait goes down further, mutation rate goes down further. On the other hand, the red bars, they represent the effect of genetic drift. When effective population size is low, then the red bars are of longer size, and that is because that is the point at which genetic drift is having a much greater effect when the effective population size is low, and vice versa. So, if this entire logic is correct, and if this indeed is the reason for which you get so much variation in mutation rate, then the prediction is that you should get a negative correlation between mutation rates and effective population size. Is this correct? So, in order to figure this out, Michael Lynch and other authors. So, Michael Lynch is the person who is the primary mover behind this particular hypothesis. So, what they did was they measured, or from the literature they figured out mutation rates in a large number of species. I think they have about 123 species, and then they also measured their effective population sizes or got the estimates, and when they plotted those effective population size on x axis, mutation rate on y axis, you can see a very nice strong negative correlation with a pretty high R square is 0.86, and as I said, this is data from 123 species ranging from bacteria to archaea to unicellular eukaryotes to invertebrates, vertebrates and vascular plants. So, that is a very broad coverage, and you can see that it is a very strong relationship. Now, over here please appreciate that I am just giving you the gist of the whole thing. The drift barrier hypothesis is a very sophisticated hypothesis. The mathematics of it is extremely nicely done by Lynch and his colleagues, and there are many papers, lot of discussion on the entire thing. I am not going into the details, the nitty-gritty gory details of that. I am just giving you the overall picture, and the overall picture is very simple. The overall picture says that the ability of natural selection to refine a phenotype is ultimately limited by the noise created by random genetic drift, which itself is a consequence of the finite population size that the particular species is experiencing. Okay. So, that is the crux of the whole matter. Now, note something over here, that in this definition you do not even see mutation rate. Okay. So, the basic principle is generic. The basic principle is applicable to any kind of phenotypic trait. The trait in the context of which Lynch et al. Have studied it in great detail is mutation rate, okay. But that does not necessarily mean that it will not apply to other places. So, one of the things that people are trying to do is to see whether in the context of other traits also this is going to be operative or not. So, this is one of those eco-evolutionary theories where ecological and evolutionary forces are coming together to tell us what is the ultimate outcome. So, we are going to stop here with this. This is where our examination of drift and its effects will end, and in the subsequent discussion we are going to talk about what are some of the other forces which can also affect evolution, and some examples thereof. So, see you in the next discussion. Bye.